Hello and welcome back to my channel DM Tricks, quality education for everyone. My name is DM Bage and today we'll explore some fascinating things about electromagnetism. We often hear that electricity and magnetism are two aspects of the same thing, electromagnetism. By the end of this video, I promise that you would never ever be able to think of them separately. You will be convinced that electricity and magnetism are not two different things, but the head and tail of the same coin, electromagnetism. Looking from one side, it appears to be electricity, while from the other side, it is magnetism. So let us explore more about this thing. In the last video, we saw that whenever a charged particle is placed in an electric field, an electric force acts on it, which is given by F is equal to QE. Also, whenever a charged particle moves in a magnetic field, then a magnetic force acts on it, which is given by F is equal to QB cross B. Now, if a charged particle moves in a region where electric and magnetic, both the kinds of field exist, then the net force acting on it will be F is equal to QE plus QB cross B, which is the summation of electric and magnetic force, and which is also the general equation for the Lorentz force. Let us consider a situation. A charged particle Q is at rest with respect to frame A and frame B, and there is a current carrying conductor having the current in the upward direction. If we look inside the current carrying conductor, we see that the free electrons are drifting in the backward direction. Since electrons are charged particles, the motion of electrons gives rise to magnetic field around the straight current carrying conductor. We also know that a straight current carrying conductor creates a concentric circular magnetic field lines around itself. The magnetic field at any point will be tangential to these circular field lines. If we take a snapshot of the current carrying conductor, we find that in any small region inside, the density of the positive and the negative charges are almost same. The free electrons are just jumping from one atom to the other. It means the current carrying conductor is neutral at any moment of time with respect to both the frames of reference. So, there is no electric field whatsoever at the location of Q, and hence no electric force is acting on Q. Similarly, the charge Q is at rest with respect to both the frames of reference. So there is no magnetic force either. So according to the Lorentz force law, no net force is acting on charge Q. So both the persons will conclude that no force is acting on charge Q. Now let us suppose that the charged particle Q starts moving at the velocity of 10 meters per second along the direction of the current. Now the charged particle is moving at the velocity of 10 meters per second with respect to both the frames. Since Q is moving in a magnetic field, a magnetic force acts on the charge Q. So both the persons will observe that an attractive magnetic force is acting on charge Q. We can find out the direction of this force by the right hand thumb rule. We find that an attractive force is acting on Q. Let us say that 10 Newton of attractive force is acting on the charge Q. Now let us suppose that the frame B starts moving at the velocity of 10 meters per second in the same direction as Q. So now Q is moving at the velocity of 10 meters per second with respect to frame A, but it is at rest with respect to frame B. But with respect to frame B, no force is acting on the charge Q, because neutral charged conductor cannot apply any electrical force, and since Q is at rest in the magnetic field with respect to frame B, no magnetic force is acting on it with respect to it. So net force acting on Q with respect to frame B is 0. But how can this be possible? It leads us to a paradox. How can the same particle be attracted and not attracted towards the current carrying conductor at the same time? There's something wrong in our reasoning. The force with respect to frame B cannot be 0. Surprisingly, the person B says that an electrical force of 10 Newton is acting on the charge Q. What is this mystery? Person A says that 10 Newton of magnetic force is acting on Q, while the person B says that 10 Newton of electrical force is acting on the charge Q. Who is right? Well, both of them are equally right. The same force appears to be magnetic with respect to the frame A and electrical with respect to the frame B. In order to understand this mystery, you need to understand length contraction. Length contraction is one of the consequences of Einstein's special theory of relativity, which postulates that nothing can move faster than the speed of light, which is kind of a cosmic limit. Whenever something moves, its length decreases in the direction of the motion with respect to the observer, and the new length is given by the relation L is equal to L naught root over 1 minus b square upon c square. The faster you move, the more significant the length contraction would be. Here, L naught is the length when the object is not moving with respect to the observer. Take a look at these illustrations. They tell you that length contraction is not some science fiction, but a very real thing. The sphere appears to be spherical when it is at rest, but as the speed approaches the speed of light, the radius in the direction of motion decreases. Similarly, the size of the rocket decreases as the speed approaches the speed of light. Now, in order to understand our mystery, you need to look inside the current carrying conductor. With respect to frame A, the positive charges are at rest or vibrating at the same place. But negative charges are moving downward or drifting downwards with a velocity of some few millimeters per second. But just for the sake of understanding, let us suppose that the negative charges are moving at the speed of 5 meters per second in the downward direction. But with respect to frame B, the positive charges are moving downward at the velocity of 10 meters per second, and the negative charges are moving downward at the velocity of 15 meters per second. Clearly, the negative charges are moving faster than the positive charges. And that causes all the difference. Since the negative charges are moving faster than the positive charges, the length contraction would be more significant in the case of negative charges, and therefore the current carrying conductor would no longer be the same for the person in the frame B. To him, the density of negative charges would be slightly greater than the density of the positive charges. So the conductor is no longer neutral anymore with respect to frame B, but it is slightly negatively charged. So now an attractive electrical force would act on Q with respect to frame B. And this explains his observation that 10 Newton of attractive electrical force is acting on the charged particle Q. Although the length contraction is very small, but even a small length contraction can cause a significant effect on electromagnetic force, because it is very strong force, about 10 to the power 36 times stronger than the gravity. On the other hand, everything is normal with respect to frame A. The current carrying conductor is still neutral with respect to frame A. So he concludes that the magnetic force is still acting on the charged particle Q. So according to frame A, 10 Newton of attractive magnetic force is acting on Q, while with respect to frame B, 10 Newton of attractive electric force is acting on Q. You see, now there is no paradox anymore. Our paradox is resolved. The charged particle will definitely be attracted towards the current carrying conductor with respect to both the frames, but it may appear as an electrical attraction with respect to one frame of reference and magnetic attraction with respect to the other. It truly tells you that electricity and magnetism are not two different things, but they are the same things. Let me give you one more example to convince you of this. Let us suppose the charged particle Q is at rest with respect to both the frames. So with respect to both the frames, the force acting on the charge Q is 0. Now let us suppose that the frame B starts moving with the velocity of 10 meters per second along the direction of the current. then the charged particle will move downward with respect to the frame B. So with respect to frame B, a repulsive magnetic force would act on charge Q. Let us say 10 Newton of repulsive force acts on charge Q. But due to the relativistic effect of the length contraction, 10 Newton of attractive electrical force would also be acting on the charge Q with respect to the frame B, so that the net electromagnetic force acting on the charge Q is still zero. So clearly, electricity and magnetism are not two different things, but the two aspects of the same thing, electromagnetism. Hope you liked the video. If you have any query, do write on the comment box below. See you again with the next video. Till then, happy physicsing. May the force be with you.